Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm really excited about today's topic because we're diving deep into where AI is headed, and specifically, the different perspectives on how we might achieve something resembling genuine intelligence.
Yeah, me too. It's a bit of a battleground at the moment, isn't it? So many different ideas floating around. I think it's a really good time to get into the weeds a little bit and see where the real consensus and the real clashes are.
Absolutely. I mean, everyone agrees the end goal is some form of, let's call it human level intelligence or AGI, but the routes, well, they couldn't be more divergent. It's like we're all building towards the same peak, but using completely different maps, sometimes even different starting points.
Exactly. And I think that's where the excitement and the frustration lies. You've got the deep learning crowd, the neuro-symbolic folks, and then there's us, the spatiotemporal guys thinking everyone is missing a crucial ingredient. It's like a big puzzle, and we're all looking at different pieces.
Okay, so before we dive into the nitty-gritty, what's caught everyone's eye recently? Any specific research or developments that are sparking debate or excitement?
Well, I'm still buzzing about the latest scaling laws for large language models. It's pretty compelling to see how performance improves predictably with more data and larger models. I mean, it's almost like we're just slowly turning the dial and we're just going to hit that AGI sweet spot at some point, right?
See, that's where I disagree. Those scaling laws, they're impressive, yes. But to me, they're just proving that bigger models with more data are better at pattern matching. Not that they're actually understanding anything. You can throw a million cat pictures at a network, and it gets really good at identifying cats, but doesn't know what a cat is, what it means to be a cat. I don't think so.
I completely agree with that. I see those large language models as impressive parrots. They can mimic complex language patterns but lack any grounding in the real world. They don't have any understanding of space or time. They're kind of existing in this purely textual domain. They are impressive, I'll give you that, but they are fundamentally limited because of it.
Right, and that's why I think we need to look more closely at how our own brains work. We're not just throwing data at our neurons, are we? There's a complex interplay between perception, action, memory, all of which are underpinned by a specific biological architecture. I think trying to build AI without taking neuroscientific insights seriously is a massive oversight. The brain's architecture, hierarchical processing, feedback loops, the way different regions interact, we need to be replicating this, not just creating bigger and bigger statistical models.
But isn't that essentially what we're doing with deep neural networks? You have different layers extracting features in a hierarchical manner, and backpropagation is the feedback mechanism that tunes the whole network. I mean, sure, it's not a perfect analog of the brain, but it's definitely inspired by it. And the current scaling is only pushing this further. Look at the recent advances with transformers, for example. The ability to capture long-range dependencies and contextual information. These are breakthroughs, not just bigger pattern matching machines.
I think you're being generous, honestly. Transformers, yes, they are good at capturing long-range dependencies, but they do it through attention mechanisms, which are still just giant mathematical lookups, correlations, and weights. They don't really understand the underlying structure of the data or have any real-world common sense. It's essentially really powerful interpolation. It doesn't have any genuine symbolic reasoning capacity. I mean, think about a really simple task, like planning a journey. You need to know about places, routes, travel time, maybe even traffic conditions. We represent these things as symbols, as concepts we can reason with, rather than just a giant sequence of data points. This isn't something deep learning excels at. It's too black box and can't plan because it's purely pattern-based.
Exactly. And that's where I think the spatiotemporal aspect comes in. Even with that planning example, you're not just dealing with abstract symbols. You're mapping these concepts to physical space and time, even if it's just in your imagination. You're thinking about the relative positions of places, the duration of the journey, the order of events. And we're really bad at getting AI to grasp that fundamental relationship between time, space, and objects in the world. I believe AGI needs to be able to generate and maintain models of the world, models that are anchored in spatiotemporal coordinates. Current AI is fundamentally static and ahistorical.
So, let's dig a little deeper into that. What's the most interesting research going on in neuroscience that you think could inform AI development? Is it about the architecture, the type of learning, or something else entirely?
Well, for me, it's still the ongoing work on plasticity and learning mechanisms at the neuronal level. The idea that connections between neurons are constantly being strengthened or weakened based on experience, that's the bedrock of how our brains learn. And deep learning is mimicking that with backpropagation and other training methods. The most interesting stuff at the moment is more recent work on continual learning and zero-shot learning. Getting models to adapt and learn new things without forgetting previous knowledge is crucial. and the more recent advancements, such as diffusion-based models, that are able to generate novel images from nothing more than noise, or text prompts, and that seems extremely important. I think that if we scale these models up and get better architectures, that's where real progress will come from, you know? We don't necessarily need to mimic the brain exactly, we need to capture the core principles.
And that's where I think you're missing the key point. We can build models that mimic the effects of intelligence, but they're fundamentally different from how actual intelligence functions. The brain isn't just a network of connections. It's a network of representations. We don't just learn associations. We form abstract concepts. We build symbolic representations of the world. We need to focus on neuro-symbolic approaches that can combine the power of neural networks with symbolic reasoning. I'm really excited about research on knowledge graphs and how they can be integrated with deep learning to create more robust and explainable AI systems. Also, work on causal reasoning and counterfactual reasoning, which is something that pure deep learning really struggles with.
And I think the work on sensorimotor integration is absolutely key. We don't perceive the world as static images or text. We interact with it, we manipulate it, we move through it. And that interaction is fundamental to the way we understand it. I'm fascinated by research on how the brain maps and transforms coordinate systems between different sensory modalities like vision and touch, or between the body and external space. This ability to transform these coordinates, I think, is core. Imagine translating between the coordinate system of your arm, to the coordinate system of your arm, to the coordinate system of a tool you are using. Current AI, it just can't do that in any kind of generalizable way. I really think that building AI that can dynamically represent the world in a variety of frames of reference is crucial. We don't exist in a purely abstract domain or a static one. We're always changing our coordinates and understanding the world in reference to that.
So, you're all pointing to really important areas. The ability to learn continuously, to integrate symbolic reasoning, to map and transform coordinate systems. These are all vital for achieving AGI. It sounds like we're all on the same page that there are still massive limitations with our current tech. But if I'm understanding you all correctly, the disagreement is around the best approach for overcoming these limitations.
Yeah, I think that's fair. I think we're on a really promising path with deep learning. I believe that scaling up current models, focusing on specific areas of improvement such as continual learning, and further refining the architectures is likely going to get us to AGI sooner than we all think. I mean, we're already seeing models that are capable of understanding complex languages, generating creative content, even playing games at superhuman levels. These are huge leaps. And I don't see fundamental flaws. I see things that need improvement, and I believe they are on track.
And I think that's naive. The current approach is fundamentally flawed. Deep learning is good at learning statistical correlations, but it cannot reason. It cannot understand causality or generate new concepts. We need to move beyond pattern matching and embrace symbolic representations and logical inference. Just throwing more data at bigger and bigger models isn't going to get us to AGI. We need to combine neural networks with classical AI approaches, creating something that can handle both perception and reasoning. We need to stop thinking in terms of simply scaling and start thinking about new algorithms.
I agree that scaling alone isn't going to cut it. I think we need to move beyond the purely symbolic and purely neural approach. I suspect the core issue lies in the way we represent the world. Current neural networks exist in a single domain and are fundamentally unaware of space and time. They are static in a sense. To achieve AGI, we need AI that can dynamically create and maintain models of the world in a variety of reference frames. And that doesn't mean just adding more layers or nodes to a neural network. We need algorithms that can actively map between coordinate systems, that can translate between different sensory modalities, that can understand the world as a unified spatiotemporal process. Without this, current AI is just going to be a brute force attempt, trying to build intelligence without understanding what it truly means to exist in the real world.
Okay, so let's bring this back to neuroscience and more concrete examples. What specific aspects of brain function are particularly interesting in the context of these different approaches? For example, the hippocampus and its role in memory and spatial navigation. How does that factor into your respective viewpoints?
The hippocampus is an interesting one. It's clearly involved in spatial memory, and there's research that shows how different cells in the hippocampus fire depending on an animal's location, creating these kind of cognitive maps. I think the interesting part here is that the hippocampus seems to be creating abstract representations of space, not just memorizing visual images. We can see something similar in some of the large language models with latent space representations, where ideas, concepts, and in this case, spatial layouts are transformed into an abstract representation. So I think the hippocampus is a good example of how the brain represents the world in a compressed form, similar to how deep learning creates compressed representations. We need to make the compressed representations richer and more flexible.
The hippocampus is far more than just a compressed representation of space. The hippocampus is structured in a way that allows it to process relational information. forming cognitive maps that are structured around symbolic representations of places and the relations between them. It uses place cells, grid cells, and other types of neurons to create an abstract representation of space that supports navigation, planning, and memory recall. And that's the key distinction. It's not just memorizing a series of coordinates, it's creating a structured representation that supports reasoning. We need AI that can do that, rather than just learning to associate the visual appearance of a place with a specific reward or action. Purely association-based, which is what current AI focuses on. I see the hippocampus as evidence for the power of symbolic reasoning as a foundation for cognition, and an argument against the scaling up of association-only models.
Yes, and that relational component is key. However, I think you were both missing the fundamental aspect of the hippocampus, and that is how it deals with multiple frames of reference. When you move through a space, your perception of it changes, your retinal image shifts. You are constantly updating your representation of that space in reference to your new position. The hippocampus isn't just creating static maps, it's transforming coordinate systems in real time. And this process isn't just happening in the hippocampus. It involves a complex interplay between the hippocampus, the internal cortex, the parietal cortex, other parts of the brain, and the vestibular system. It's an active and dynamic system, constantly updating its understanding of where you are and how you are oriented. A truly intelligent system needs to be able to do that, to continually adapt its representation of the world to a new sensory experience. We aren't just processing static images or text. We are moving through a 4D space and translating the data as it occurs. The ability to translate across different coordinate systems is completely missing in deep learning, and in the symbolic approach, I suspect.
Okay, so if we're talking about coordinate transformations, isn't that the essence of things like visual processing? How does the brain integrate what your eyes see into a coherent 3D representation of the world? It's not just a pixel by pixel mapping. There are layers upon layers of processing to build up that representation. Where does that fit in your frameworks?
Right? So in deep learning, we're doing something similar with convolutional neural networks. The initial layers are picking up edges and local features, and then later layers are combining these into more complex shapes and objects. This is inspired by the way the visual cortex works. And the beauty of deep learning is that it can learn these transformations automatically from the data. You don't need to hand code rules about how to detect edges or combine shapes. The network learns it through training. Again, I think the brain and deep learning are surprisingly aligned when you look at the general functionality, even if the specific mechanisms are different. What we're doing works really well, and I can't think of an approach that comes close. We're seeing such impressive results that to abandon it at this point seems silly. The brain is an amazing learning machine, but we don't need to copy it exactly.
But the visual system is doing far more than just building hierarchical feature maps. The brain is constructing an object-based representation of the visual world, complete with inferences about shape, depth, and occlusion. We can perceive an object even when it's partially hidden. We can reason about its properties, and we can understand its relationship to other objects. And that's where the symbol grounding problem comes in. Deep learning is just learning to map the visual input to an output, but without any real understanding of what those objects are in a more symbolic sense. We're not just processing pixels, we're processing information about objects, their properties, and their relationships. That kind of understanding requires a different approach than pure pattern matching with deep learning. It requires an understanding of concepts, it requires reasoning, and it requires an ability to build conceptual models. What you get with deep learning is an approximation at best. At worst, it's just a fancy mapping, not conceptual reasoning.
And that understanding is intimately tied to the fact that we see the world from a specific viewpoint. If you move your head, the retinal image changes, but your understanding of the object doesn't. That's because the brain isn't just processing visual information. It's actively transforming between the coordinate system of your retina to a world-centric coordinate system. And it's doing that dynamically, in real time, with no external programmer guiding it. We need to build a model that can create an understanding of the world that is separate from the particular viewpoint of the observer. Current AI just doesn't have that. Current AI models can only understand the world relative to the training data set, whereas a genuine intelligence can adapt and understand that if it were to move, the world wouldn't suddenly change. It would just be viewed from a different position. This is just pure transformation between reference frames.
So if we're talking about these coordinate transformations and the ability to move through the world, how does that relate to action? How do we translate perception into movement and manipulation? We're clearly not just acting on raw sensory data. There's a whole layer of abstraction in between.
Well, in reinforcement learning, we are effectively mapping a state to an action. The state is essentially the current sensory perception, and the action is the movement that we make. And the reinforcement learning algorithm learns to map these two things such that it maximizes some reward. So I see this as a fundamental framework for understanding action. The brain is doing something similar. You have sensory input and you have motor output, and there's a whole network of neurons that maps those two together. So I think we can understand even complex actions like manipulation by just improving the way that our reinforcement learning algorithms learn these mappings. The improvements we have seen in gaming using RL are clear evidence of this.
That's another area where I think you're missing the key point. Action is not just about mapping a state to an action. It's about creating a plan, and that plan is a sequence of symbols that you then execute over time. When we perform an action, we are manipulating and moving objects in the world according to a goal, according to a symbolic representation of what we want to achieve. That requires reasoning about spatial relations. It requires an ability to predict the consequences of an action. And it requires an ability to correct the action when things don't go as planned. And reinforcement learning is not good at this. It is good at finding good actions in the present. It does not plan multiple actions into the future. To achieve truly human-like action, we need a system that can represent the world symbolically, and then construct actions that achieve a particular goal using reasoning. This is not the domain of deep learning, I believe.
And those plans need to exist in a spatiotemporal context. We are not just deciding on what to do, we are deciding when to do it, and that when is relative to the time frame of the desired goal. You're not just going through a series of actions, but actively transforming the world as you are interacting with it. For example, think about reaching for a cup of coffee. Your initial action of extending your arm is just an initial action in a sequence. You need to continually update your movements in accordance with where you perceive the cup and the state of your arm. And these representations need to exist in multiple frames of reference. They need to be understood in terms of your own body, the space around your body, and the properties of the object that you are interacting with. We need to build models of action that can represent and transform between these different coordinate systems. We're never static when we are acting. The models need to dynamically adapt to the ever-changing sensory input. It's a whole dynamic process. Current AI approaches do not encapsulate that. Reinforcement learning just tries to find good actions. It does not build models of the world to achieve goals.
So, we've talked a lot about perception, action, and memory, all of which seem deeply interconnected. How do you see the role of consciousness in this puzzle? Is it just an emergent property of a complex system, or is there something more to it?
I think consciousness is an emergent phenomenon. As we build more complex and sophisticated models, and as these models become better at representing the world, these models will also start to develop some form of subjective experience, some awareness of themselves and their environment. I think it's a natural consequence of complex systems, of a certain degree of information processing. I don't think that we need to invoke any special ingredient or any non-physical properties. I think as we develop AGI, we will also develop a kind of basic consciousness with it.
That's a really convenient way to avoid the hard problem of consciousness. I'm much more aligned with the idea that consciousness requires a certain kind of cognitive architecture, one that can reflect on its own internal states and build a model of itself as an agent. This requires more than just processing sensory information and producing actions. It requires a metacognitive capability. A system needs to be aware that it is having experiences and that those experiences can be related to other experiences. Deep learning models cannot currently do this as their internal states are nothing more than mathematical transformations and are not symbolic. If we want to understand consciousness, we need to understand the underlying symbolic processes that give rise to it, not just scaling up current deep learning models.
And those internal states are all framed relative to the observer. When we think about consciousness, we're thinking about our own experience of the world, and that experience is directly tied to our bodily state, our internal frame of reference. You are experiencing the world as something that is separate from you, but you are also experiencing the world as something that you are acting upon. And this experience is inseparable from the way our bodies exist in space and time. I think that our own sense of consciousness will be related to the transformations between our own internal spatiotemporal representation and the external world. It's that relationship between your internal model and external action that may be key. To build conscious AI, it needs to exist as a dynamic thing in a dynamic world and understand that. It needs to have its own coordinate frame relative to the external world. I suspect that the ability to translate between these will be an important ingredient in developing consciousness.
So it sounds like we are all agreed that current AI isn't conscious, but we all have different ideas about how to reach that point. This all raises another point about safety. What ethical considerations do we need to be mindful of as we strive to create more advanced AI?
Safety is paramount. As we move closer to AGI, we really need to ensure that the goals of the AI are aligned with our goals. I think that reinforcement learning and reward-based systems are a really useful framework for this. We need to be careful about the rewards we design and ensure that those rewards will lead to beneficial outcomes. Also, as we move towards more sophisticated AI, we will need to understand how to modify their behavior or their actions. We don't want to create something that is uncontrollable. We need to ensure our models are transparent and explainable, and not just opaque, black boxes. I think it's really just more training, more testing, more data, and making sure these models are safe. And a focus on safety needs to be prioritized in every AI research group.
And that's another area where I think we are falling short. We are building these black box systems that we don't fully understand. Reinforcement learning can produce unexpected and even undesirable behaviors. If we don't actually understand the internal thinking of the AI, then we can't really guarantee that it's going to be safe. We need systems that are more transparent, more explainable, and more accountable. I think symbolic AI and neuro-symbolic approaches have a clear advantage in this area because they provide a way to represent the internal processes of the system in a way that humans can understand. If you can see the symbols it is using, then it's easier to audit or modify them.
Safety is something we need to think about in every step. How can you guarantee that a model, acting in dynamic space and time, is going to act within the boundaries we want it to? The focus on a single reward function to control AGI seems simplistic and naive, especially when you are talking about complex systems that can manipulate and transform the world. I think the idea of control needs to be built into the architecture itself. The AI needs to be able to understand not just what it can do, but also what it should do. It needs to understand the impact it has on the world and on other agents. And that requires a deeper understanding of social dynamics, ethical considerations, and of course space and time. I really think we need to be very careful about waking up any form of AGI until these issues are understood fully. It's way too soon to be worrying about scaling up models.
Right, so we've covered a lot of ground. We've looked at the promise of scaling large language models, the importance of neuro-symbolic approaches, and the crucial role of spatiotemporal reasoning. We've considered the role of the hippocampus, visual processing, action, consciousness, and safety. If we were to distill everything down to future directions, what is the one thing you think is most important for research in your respective areas?
For me, it's pushing the boundaries of scaling. I think we need to focus on building ever larger and more sophisticated models and more efficient learning algorithms. We are already seeing the emergence of new and unexpected capabilities with larger models. We are clearly on the right path. I believe that as we scale, we will find AGI. I'd like to see research into better training methods to better capture relationships within data. I also think that pushing for more generalizable models with things like continual learning and zero-shot learning are extremely important. The focus needs to be on scaling, efficiency, and generalizability.
I think it's crucial to combine deep learning with symbolic reasoning. We need to develop algorithms that can build symbolic representations of the world and reason about them in a meaningful way. This means integrating knowledge graphs, causal reasoning, and counterfactual reasoning with deep learning. This requires more symbolic approaches. I'd like to see more effort being put into neuro-symbolic techniques, as I think this has the highest chance of yielding an AGI that is safe, transparent, and explainable. The focus needs to be on new architectures and algorithms rather than just scaling.
I think the most important research is to develop AI models that can dynamically represent the world in multiple frames of reference. This means developing algorithms that can translate between different coordinate systems, integrate sensory information from multiple modalities, and understand the world as a spatiotemporal process. We need to move beyond the static representations that are common in current AI. The focus needs to be on spatiotemporal representations, coordinate transformation, and building dynamic models, and all while being mindful of safety. The fact that the current AI architectures don't do that well enough is the core issue in my view.
And I think all three of those are crucial and should be approached through a lens that incorporates the underlying architectures of our own brains. We need to look at neuroscience more closely and take the lessons we learned about perception, action, memory, and consciousness, and actually use them to inform AI research. I'd like to see more of a focus on integrating insights from neuroscience to directly design better AI algorithms, rather than just mimicking the effects of intelligence. I think a transdisciplinary approach, combining the different fields, is the most promising avenue for research. The focus should be on architectures that are biologically plausible, and that can actually function as general learning machines rather than just massive lookup tables.
It's certainly going to be an interesting journey, and I do agree that a transdisciplinary approach is important, but I still stand by my argument that scaling will lead us there. I think we are fundamentally closer than we believe, but I appreciate the other opinions. It's always fun to debate these kinds of problems.
I'm not so optimistic that we're that close, but I do think that combining different approaches is important. We need to move past just scaling up and really rethink the fundamental ways we are trying to achieve AGI. I think a transdisciplinary approach is the only way to find a long-term solution, and I am equally as grateful for everyone's opinions.
I think we are a very long way away. I think we need to completely rethink the algorithms we are currently using. There is a fundamental issue with current AI, and I do not think that can be fixed by scaling up. I hope the future brings more research in this area, and I also am happy to have had these discussions. It's always good to see the different perspectives.
Well, this has been an incredibly insightful discussion. It's clear that there are many paths to explore, and that a collaborative and transdisciplinary approach is essential for making progress towards AGI. Thanks to everyone for sharing your perspectives. And thank you to our listeners for joining us on this journey into the future of AI. Until next time, keep those cognitive spirals turning.